Welcome back, focused learners. Today, on The Explainer, we're tackling something that, let's be honest, usually sparks a bit of dread. Yeah, we're looking at that massive sheet of physics formulas, but we're going to transform it into an organized, highly effective diagnostic toolkit. If you've ever felt completely overwhelmed by the sheer volume of equations you need to memorize for your tests, you are in exactly the right place. We're going to decode how the universe works, literally one formula at a time. And hey, quick reminder before we jump in. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Let's get into it. Okay, so staring at this dense wall of general physics equations can definitely induce panic. I totally get it. It looks like a random alphabet soup of letters and symbols, right? But here is the secret. It's not random at all. Instead of viewing this as just another miserable memorization chore, we're going to break it down logically. I want you to think of this document not as a boring textbook page, but more like a pegboard in a master mechanic's garage. Every single tool has its specific place and, more importantly, its specific job. And here's the second half of our source material. This takes us through thermal physics, waves, electricity, and even out into space. Again, I know it looks like a lot, but every single equation you see here serves a very specific, totally understandable purpose once it's categorized correctly. By the time we finish this explainer, you're going to know exactly which mental shelf to reach for when you're faced with a tough physics problem.
So, here's our roadmap for today. First, we'll cover core mechanics. Next, thermal and waves. Then, we'll hit circuits and electricity. And finally, space, area, and volume.
All right, let's dive right into Section 1, Core Mechanics and General Physics.
So, these foundational equations govern the everyday movement of physical objects, the stuff you can actually see and touch. They help us measure fundamental forces, mass, and velocities. And look at how beautifully they build on each other. We start with simple movement, right? Speed, or v, is literally just distance over time, s over t. But if that speed changes, boom, we need acceleration. A equals final velocity, v, minus initial velocity, u, all divided by time. Then we bring mass into the picture. Weight is just mass times gravitational field strength. Density, which is denoted by the Greek letter rho, by the way, is mass divided by volume. And when things push or pull, we get force equals mass times acceleration, the legendary F equals ma. We've even got the spring constant, k, which is force per unit extension. Think of this as your core toolkit for things that move, stretch, and weigh us down.
Now watch how this builds into the energy transferred by those forces. Once an object is moving, it has kinetic energy, which we calculate as 1/2 mass times velocity squared. If you lift that object up, you get a change in gravitational potential energy, or mass times gravity times the change in height. The crucial takeaway here is that forces do work. Mechanical work done, W, is simply force times the distance moved. And how fast are you doing that work? Well, that's power, the change in energy, or work done, divided by the time taken. We also see efficiency here, which is just useful power output over total power input, and pressure, which is force spread out over an area.
Okay, really quick, notice the little greater than symbol here. Our source specifically flags these equations with a greater than sign to denote supplementary content for the extended syllabus. So if you're an advanced student aiming for those top grades, these are your extra tools. You get impulse, which is force times time, and that perfectly balances out as the change in momentum, mass times final velocity minus mass times initial velocity. You also get the change in pressure formula for fluids, which is density times gravitational field strength times the change in depth.
Moving on to Section 2, Thermal and Wave Properties.
All right, we've mastered the visible world of blocks and springs, so let's shift gears to the invisible phenomena: heat, light, and sound. Have you ever wondered exactly how much energy it takes to boil a specific amount of water? Or why, say, some metals heat up way faster than others? Pose this question to yourself right now. How do we actually measure the energy required to change temperature?
Well, specific heat capacity, represented by the letter C, gives us exactly that. It's the energy required, delta E, divided by the mass times the temperature increase, which is delta theta. It essentially quantifies the exact energy needed for temperature shifts per unit mass. Oh, and this section also reminds us of an absolutely crucial conversion between Celsius and Kelvin. Just add 273 to your Celsius reading. Plus, we've got the foundational gas law rule here. Pressure times volume equals a constant.
Grouping the light and sound equations together, we can really see how they interlock. A wave's velocity is simply its frequency times its wavelength. When light hits a mirror, the angle of incidence exactly equals the angle of reflection. Simple enough, right? But when light travels through different mediums, like from air into water, it bends. We measure this bending with the refractive index, n, which is the ratio of the sine of the angle of incidence to the sine of the angle of refraction. Or, alternatively, it's just the reciprocal of the sine of the critical angle.
Next up, Section 3, Circuits and Electricity. Now, this section is packed with crucial proportional relationships that govern the flow of electrons. But first, we really need to clear up a common point of confusion. Remember how we saw W for work done in the mechanics section as force times distance? Well, here in electricity, electrical work done is equal to energy transferred, so W equals delta E. It is absolutely vital to explicitly contrast these two contexts. You have to clearly understand your scenario to know which formula to apply to that shared variable W.
Check out how the resistance math completely flips depending on the physical layout of your circuit. If your resistors are lined up in a single path, a series, you just add them right up. Total resistance equals R1 plus R2. Easy. But if they branch out in parallel, the total resistance actually drops, and we have to use the reciprocal formula. 1 over total resistance equals 1 over R1 plus 1 over R2.
Before we go further, if you're finding this helpful, make sure to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Okay, here is the relational bridging for core electricity. Electromotive force, or EMS, is electrical work done per unit charge, so V equals W over Q. Current, I, is the charge flowing over time, Q over T. Resistance is potential difference over current, R equals V over I. And look at how power bridges the gap. Power equals current times potential difference, P equals IV. If you want the total energy, you just multiply that power by time, giving you E equals IVT. It is just a perfectly logical chain of electron flow.
And we definitely can't forget our sub-toolkit for power transmission. For transformers, the ratio of primary to secondary potential differences exactly matches the ratio of turns on their respective coils. Assuming perfect efficiency, the current times potential difference across the primary equals the exact same across the secondary. And when we're sending that power across long cables, the power loss equals current squared times resistance.
Finally, we arrive at Section 4, Space, Area, and Volume.
Let's expand our scale all the way out to the cosmos. I know space physics might sound super intimidating, but honestly, it's just an extension of what we already know. How do we calculate the speed of objects orbiting in space? We just use a modification of fundamental circular motion. Average orbital speed v is simply the circumference of the orbit, 2 pi r, divided by the time period, t. See? Not so scary. Here's another extended syllabus marker for you advanced learners out there. We use the Hubble constant, h0, which is calculated as the speed a galaxy is moving away from Earth, v, divided by its distance, d. And this brilliantly illustrates just how interconnected physics really is. Get this, by simply taking the reciprocal of the Hubble constant, distance over velocity, we actually get an approximation for the exact age of the universe. How cool is that?
And to close out our toolkit, here's a rapid-fire reminder of your mathematical prerequisites. The area of a rectangle is length times breadth. A triangle is half base times height. A circle is pi r squared. For volume, a cuboid is length times width times height, and a cylinder is pi r squared times height. Now, why are these even here? Because they are the essential building blocks for calculating those complex physics metrics like pressure and density that we talked about at the very beginning of the explainer.
And there you have it, guys. We've taken a massive, intimidating wall of text and organized it into a structured, highly effective toolkit. Remember, these equations aren't just random letters meant to be memorized for some test. They are the exact, specific tools used by scientists to decode how the entire universe works, from a falling apple all the way to the age of the cosmos itself. So, armed with this brand new toolkit, which physics mystery will you decode first? Thanks so much for joining me on this explainer. Keep learning, and as always, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Catch you next time.